Good morning, myself Sukhvinder from Government Polytechnic College for Girls, Patiala, here to present a lecture on Central Processing Unit, that is a topic under computer architecture, that is subject of 4th semester IT. So, first we will study what is a computer. Computer is an electronic device operating under the control of instructions, the software instructions stored in its own memory unit that can accept data, that is also known as input, manipulate that data, that is manipulation of the data is known as process, and produce information in the form of output from the processing. Generally, the term is used to describe a collection of devices that function together as a system to perform some operations. Computer system is a collection of devices. Devices for the computer system are input devices, output devices, and the processing unit. In these devices, there are some categorized devices. First is monitor, speaker. Monitor is an output device. Speaker is also an output device, and printer is an also output device, that is hard copy output device. And scanner is an input device. Keyboard is input device, that is for key for input, and then mouse is a pointing device, that is input device. And in CPU we have processors, memories, and storage devices, that are CD writer, readable, writable, and floppy, hard disk, and others. So now we will study what does a computer do. Computer can perform 4 general operations which comprise the information processing cycles. First is part of the computer systems are input devices, process, output, and storage. Input is the process of taking data from outside, and process is the performing the functions or operations on that data, and output is the processed form of data, and the storage is to store results and data. Now first we will study what is data and information. All computer processing requires data. Data means which is the collection of raw facts, figures, and symbols, such a number, words, images, videos, and sound given to the computer during the input phase. Computer manipulate data to create information. Information is data that is organized, meaningful, and useful. During the output phase, the information that has been created is put into some form, such as a printed report or in soft copy on the monitor screen. The information can also be put in computer storage for further use. So, in short, we can say information is the processed form of data. So, now why is a computer so powerful? First, the ability to perform the information processing cycle with amazing speed. It means in some short period of time we can do multiple operations. And reliability, low failure rate, it means whatever we want to do is reliable. And accuracy, the ability to store huge amount of data and information in storage devices. And ability to communicate with other computers used through a network. Now we will study primary components of a computer. Input devices, central processing unit that contains control unit and the arithmetic logic unit, memory, and output devices, and storage devices. Now we will you see that there is a diagrammatical view of the computer system. In this we have input devices, memory, output devices, storage devices, and central processing unit. We take data from outside using input devices. Through input devices, process that data using central processing unit, that is that contains a control unit and arithmetic logic unit. Control unit controls the operation of the CPU, and arithmetic logic unit perform the arithmetic operations like addition, subtraction, multiplication, and other arithmetic or mathematical operations. And we can store the results in memory and in storage devices, and then we will produce then the computer produce results as to the output devices. The central processing unit. So the main topic of today's lecture is the central processing unit. We will study it in deeply. The central processing unit contains electronic circuits that causes processing to occur. The CPU interprets instructions to the computer, perform the logical and arithmetic processing operations, and causes the input and output operations to occur. It is considered the brain of the computer. All the arithmetic operations and other controlling operations are performed in the CPU, that is central processing unit. First is the stack. What is the stack organization? First we will study what is a stack. Stack is a last in first out data structure, a storage device that stores information in such a manner that the item stored last in the is the first item to be removed or retrieved, is known as stack. Is also called last in first out, that is also called LIFO list, useful for compound arithmetic operations and nested subroutine calls. So we can say in this diagram, first arrow represent the top of the stack. We can insert the element at the top of stack, and we can also remove the element from the top of the stack. Now the stack organization, there are three concepts. First is stack pointer. Stack point, that is also known as SP, a register that holds the address of the top item is the in the stack. SP always point at the top item in the stack. So what is SP? SP is a register where we store the address of the top pointer, means last item which we can remove and where we can insert a item. There are main two operations that can be performed on the stack. This is push and pop. Operations to insert an item into the stack is known as push, and pop operation is known for the operation to retrieve an item from the stack, or we can say remove an item from the stack. This is a diagrammatic view of a register stack. A stack can be organized as a collection of finite number of registers. We can store data in registers and maintain those registers in the form of stack. Where SP is the stack pointer that represents the top of the stack. Top means where we can insert or remove elements, and there are two more registers, full and empty. Where full in 64-bit 4-word stack, the stack pointer contains 6 bits. The 1-bit register full is set to 1 when the stack is full. When full register will always represent 1 when the stack is full and there is no space to insert any other elements in the stack. Empty register is 1 when the stack is empty and we can insert the number of elements in the stack. The data register DR holds the data to be written into or read from the stack. So DR is always act as a temporary register where we can store the element after removing from the stack, or we can store the element which we want to insert in the stack. In this example, there are registers. There is a stack having 64 words from 0 to 63, and in the word 1, 2, 3 there are 3 elements, A, B and C, and at the top SP, where SP points to the third location, that is 3, where C we can remove this element from the stack and we can insert at the 4th position in the stack. Now we will study what is instruction format. The most common field in instruction formats are first is mod field, second is operation code, and third is address field. Mod field specifies the way the effective address is determined, that what the addressing mode is being used in the instruction. And the second is operation code. It represents the code of the operation which we want to perform on the data. And the third is address field, designates a memory address or a processor register. In address field, most of the times in many instructions represents the address where the data is stored on which operations to be performed. This is the simple view of instruction: mode, opcode and address. First field shows the mode of the instruction, second is opcode, means operation code, and third is the address of the variables. There are types of instruction formats. First is zero address instruction. Stack is used arithmetic operations, pops 2 operands from the stack and the push the results. It is known as zero address instruction because in this format we do not use any address. There is only one stack. From the top of stack, 2 items will be removed or any one item will be removed and the operation will be performed on that item. So we no need to specify any address of the location from where we want to take the operands. Operands are the variables on which we want to perform the operation. Second is one address instruction. AC and memory. AC is known as accumulator, and memory. Since the accumulator always provide one operand, only one memory address need to be specified. The operation will be performed on the two variables. One is stored in the accumulator and one is in the memory. So we need one memory location. That's why this instruction format is known as one address instruction. Next is two address instruction. Two address registers or two memory locations are specified, one for the final result. So for any operation where we have two operands, we need one memory location and one accumulator. But in two address instruction, we use two memory locations. Second memory location is used to store the result of the operation. In one address instruction, result is again stored in the accumulator. Next is the three address instruction. In these formats, three address registers or memory locations are specified, one for the final result. It is called general address organization. Now what does an instruction format includes? An instruction format includes layout of bits in an instruction. Second is it includes opcodes, that is operation code. Operation code is the code provided for every operation to be performed on any data. It includes implicit or explicit operands. Operands means that is data on which the operation is to be performed. Usually more than one instruction format in an instruction set. Now what are the factors that affects an instruction length? Affected by the effects, first is memory size, second is memory organization, third is bus structure, which is followed by the CPU, and the CPU complexity and the speed of the CPU. Trade-off between powerful instruction reprocessors and saving space. Now how the bits are allocated in instruction formats. These factors are number of addressing modes, number of operands. Addressing modes are the modes of saving data or operands in the memory or representing data. Second is number of operands. These are the number of variables on which data is to be performed. Register versus memory. Number of register sets means how many registers are being used, and address range. It depends upon the size of memory, and address granularity. Now we will study instruction format. In instruction format, first field is opcode, that is known as operation code. 0 to 8 bits represent operation code, then 9 to 12 bits represent registers, and next one bit represents indirect bit, and then index register, and the last field from 18 to 35, it represents a memory address. The total instruction format is combined of 0 to 35 bits, it means total 36 bits. Now we will study addressing modes. What are addressing modes? There are following addressing modes which are available in computer architecture. Basic addressing modes. First is immediate addressing mode, direct addressing mode, indirect addressing mode, register addressing mode, register indirect addressing mode, displacement or also known as indexed addressing mode, and stack addressing mode. First we will study immediate addressing mode. Operand is part of the instruction. In immediate addressing mode, operand is stored in instruction itself. Operand is equal to address field. It means, for example, we have an instruction add 5. Here add is an operation, that is opcode. Add 5 to the contents of accumulator. 5 is an operand. In this instruction, 5 will be added to the contents of the accumulator. Whatever will be the result will be stored in an accumulator. No memory reference to fetch data. It is fastest addressing mode in the computer architecture and limited range. Now immediate addressing mode can be represented in diagrammatic view. Suppose we have this instruction and we have only two parts. First is opcode, that represent the operation code. It represents the operation to be performed on the operand. Operand is the variable on which operation to be performed with accumulator. Now we will study direct addressing mode. Address field contains address of operands. Effective address is equal to address field. For example, we have an operation add A. Add contents of cell A to accumulator. Look in memory at address A for operands. Single memory reference to access data. No additional calculations to work out effective address, because there is a direct processing. The contents of A are added to the contents of accumulator, and limited address space is used. So it is a diagrammatic view. In the direct addressing mode, we have the operand itself stored in the instruction, but in this direct addressing mode, opcode first, then in second part there is no operand, there is address of the operand. That operand is stored in anywhere else in the memory. So the second part of the address represent the address of the operand. Now we will study indirect addressing mode. Memory cell pointed to by address field contain the address of pointer to the operand. It means there is another pointer in the memory that points to the operand. Effective address is equal to A. You can find address A and look there for operands. For example, add A, add contents of cell pointed to by contents of A to the accumulator. This is the diagrammatic view of the indirect addressing mode. First, in this instruction, first is the opcode. In all the instructions, first is the always opcode, that is operation code, that represents the operation to be performed, and second is the address of the variable A. This address of a memory location. In that memory location, again there is a pointer to the operand. So the actual address is not given in the instruction, but address of that address is given in this instruction, and the pointer to that operand is in any other memory location. This is a register addressing. Operand is held in register named in address field. Effective address is equal to register. In this we have a register and we store address in that register. Limited number of registers are used. Very small address field needed, because address field requires only the address of the register. Very small address field needed means shorter instructions, means it takes less memory space and faster instruction fetch, because if the size of instruction is short, then it can be fetched fast. In register addressing, no memory access is required, very fast execution, very limited address space, and multiple registers help performance, requires good assembly programming or compiler writing. This is the diagram for register addressing mode. In instruction, first is the opcode, second is the register address, and in that register the operand is stored. So there is no memory location is required. The address part of the instruction stores the address of register, not any memory location, and in this register operand is stored, and we can the instruction can fetch that operand from the register, from the given register. Indirect addressing mode, effective address is equal to R. It means we no need of any calculation. Directly we can access the register that is given in the address location, and operands is in memory cell pointed to by contents of register R, and larger address space, that is 2 raised to power n. One fewer memory access than indirect addressing. Register indirect addressing diagram, we can say that it is instruction format. First is the opcode. Always in any instruction, first part is the opcode, that is operation code, and the second part is the according to the addressing mode. In this addressing mode, it is the address of a register, and in that register address of a memory location is stored, and that points to the operand in memory location. So it means, and that's why it is known as indirect addressing, register indirect addressing mode, because one register in instruction the address of register, and in that register is the address of operand, and in that memory location operand is stored, and from that memory location instruction can fetch the operand. There is a displacement address. In this effective address is calculated by addition of address field plus register, where A is the base value. Two fields, address field had two values. First is base value and R is the register that holds the displacement or vice versa. So this is the operation displacement addressing mode. First is operation code. Second, in second field there are two parts. First is register R, second is address A. So the operation is performed is registers address take the pointers to operand, and that address is added to the operand in the memory location, and this is known as displacement addressing mode. Next is relative addressing. A version of displacement addressing. R is is equal to program counter, that is also known as PC, and the effective address is calculated by A plus PC. That is get operands from A cell from current location pointed to by program counter, and locality of reference and cache uses. Now we will discuss what is a base register addressing. It holds displacements. A holds displacements. R hold pointer to base address. R may be explicit or implicit. Segment registers in 8086. Index addressing, in this A is equal to base value, R is equal to displacement, and this address is calculated by effective address is equal to A plus R, where A is in the base value and R is the displacement, as we have studied what is base value and the displacement addressing mode. Next we will study stack addressing. As we have already studied what is stack. Stack is a list of elements in which we can perform operations on the top of stack, and we can remove items from the top of stack, and we can insert items on the top of the stack. Operands are on the top of the stack. For example, add, pop two top two items from the stack and add. It means if we will perform add operations on the stack, we are taking top two values from the stack and performing the operation on that those elements. Pop means removing elements from the stack, and push means adding element to the stack. So these were the addressing modes, and now we will study what is a RISC. RISC is the reduced instruction set computer. Use of simple instructions in these architectures. One of their key realization was that a sequence of simple instructions produces the same results as a sequence of complex instructions, but can be implemented with the simpler and faster hardware design. Reduced instruction set computers, that is RISC machine. Addressing modes used in RISC are limited number of addressing modes are used. The effective address is computed in a single clock cycle, so that's why it is a fast architecture. There are some characteristics of RISC computers. Simple instruction set. In RISC there are instruction sets that are not complex. Very simple instruction and easy to understand instruction sets are used. In a RISC machine, the instruction set contain simple basic instructions from which more complex instructions can be composed. Same length instructions, it means how many the number of instructions used all are of the same length. There are some more characteristics of RISC. Each instruction is the same length, so that it may be fetched in a single operation. So if we have the instructions having same length, same number of bits, these instructions can be fetched in a single cycle, because all the requirements and the variables are all are the same for the operations. One machine cycle instructions are used. Most instructions complete in one machine cycle, which allows the processor to handle several instructions at the same time. This pipelining is a key technique used to speed up the RISC machines. Reduced basic purpose was to design a RISC architecture is to reduce the number of instructions and to save the memory space for this designing. There are some advantages of RISC. First is the speed. Since a simplified instruction set allows for a pipeline, superscalar design, RISC processor often achieve 2 to 4 times the performance of CISC processors using comparable semiconductor technology and the same clock rates. So this point represents that RISCs are basically designed to speed up the processing of a computer, and there were superscalar designs were used in RISC to achieve 2 to 4 times the performance of a CISC. CISC is a also an architecture, computer architecture, that is complex instruction set computers, and in the comparison of these CISC systems, RISC were developed to increase the performance of the systems. It is 2 to 4 times the performance is increased. Next point is the simpler hardware. Because the instruction set of a RISC processor is so simple, it uses up much less chip space. Extra functions such as memory management units or floating point arithmetic units can also be placed on the same chip. Smaller chip allows a semiconductor manufacturers to place more parts on a single silicon wafer, which can lower the per chip cost dramatically. It means it is a feasible system that can be adopted by any it is a low cost system that can be adopted by any organization. Shorter design cycle. Since RISC, that is reduced instruction set computer processors, are simpler than corresponding CISC processors, they can be designed more quickly and can take advantage of other technological development than corresponding CISC designs, leading to greater leaps in performance between generations. Now we will study the CISC, that is complex instruction set computers, as compared to the reduced instruction set computers. A complex instruction set computer, pronounced as CISC, SISK, CISC, is a microprocessor instruction set architecture, in which each instruction can execute several low-level operations such as load from memory and arithmetic operations and a memory store, all in a single instruction. It means all the operations that are performed in the computer are performed in a single instruction. We are taking input, processing data, and storing that and producing as an output that information. So first we will study the main idea of the CISC. The philosophy behind it is that hardware is always faster than software. Therefore, one should make a powerful instruction set which provide programmer with assembly instructions to do a lot with short programs. So we all know what is a machine. Machine cannot understand the value or a language spoken by or written by a human being. So we can understand a high level language. A user or any programmer use high level language, and the machine can understand the low level language at the bit level, and that is in zeros and ones. So the instruction format, those we have studied in the last slides, those are used to provide the information or to store the instructions in the form that is understandable by the computer. So in CISC, one should make a powerful instruction set which provide programmer with assembly instructions. Assembly is the low level language that is understandable by the machine language. So there is a low level language and a high level language, and the assembly language is the intermediate language between the low level language and the high level language. High level language is used and understood by the user or a programmer, and the machine or a computer system understand the low level language, that is also known as machine language. In many programming languages, this is known as the machine code or an object code. So the primary goal of the CISC is to complete a task in few lines of assembly instructions as possible. So it is to reduce the complex instruction set. It means less number of instructions and most operations are performed. Memory in those days was expensive, bigger problem, more storage, more money, hence needed to reduce the number of instructions per program. So with less number of instructions, more operations to be performed. Number of instructions are reduced by having multiple operations within a single instruction. In one instruction, multiple opcodes are given and multiple operations are performed in single instruction in one line. That's why this architecture is known as complex instruction set, because it is not easy to understand multiple operations in a single line.